Welcome back to part 2 of our series, Design a Product With Us. Last week we scoped the chip, which was the PCA 9685 PWM driver chip. We've got it on a breakout board here. I've just assembled the PWM headers for a servo. I've connected it to the Raspberry Pi Pico using the PicoDev connector, just a breakout lead that goes to the header. And we've got a servo and external battery power so that we can drive the servo. We're just going to focus on getting a hello world running on this chip from scratch. So we'll bust out MicroPython and write, I guess, a simple class to control this PWM driver. I'm not going to build it from the ground up as a PicoDev project. We'll rather start how any other maker would, by creating an I2C object and sending some bytes over the bus. The stuff that makes it compatible with PicoDev is more of like administrative wrapping stuff that we can probably do later at the end. But for now, we'll just get a hello world running. So I have a blank working environment in Thonny. We have the datasheet for the chip, armed with nothing more than these things. We're going to drive a servo. Let's get started. We'll begin like every great project does. Let's create a new file. Class PCA 9685, and we'll need an init. I know that we'll pass in an I2C bus or an I2C object, so we'll need that. And the default address for the chip is hex 40. We know this because Adafruit have been very generous with how they have laid out this board. There's an address jumper. Remember, there's 6 address pins on this device, and here are the jumpers. And Adafruit have laid it out such that we can just infer the address from this. We have a 1 followed by 6 open jumpers. So that's a 1 followed by 6 zeros, which is hex 40. And so our class will take in that self I2C is equal to I2C. It'll take in that I2C object. Self.address will be set to that address value. And now what? Well, we have to actually invoke our class in some kind of script, and I'll just work in the same file for now. We can pull things apart into separate documents later, but for now I think it makes sense to just keep everything together. So we can write our script. We're working on a Raspberry Pi Pico, so of course from machine import, we'll need to import I2C, and we'll also need pin. The PicoDev expansion board for Raspberry Pi Pico uses pins, or GPIO 8 and 9, for the PicoDev connector. So we'll need to define those pins. SDA is pin 8, and SCL is pin 9. And we'll create our I2C object. I2C equals I2C, the bus number. We're working with bus 0. Then SDA equals SDA, SCL equals SCL. Done. Now we're going to initialize the driver. We'll create an instance of this class. So we'll just say, I guess we'll just call it the driver equals PCA 9685. And we need to pass in the I2C definition. And actually that's everything, because the address has a default value. So to begin with, we have a class definition that doesn't actually do anything on the I2C bus yet. It just creates an instance that has an I2C definition and some address. And we've just set up our microcontroller with the I2C bus and created an instance of that class called driver. Now we have to actually interact with the physical hardware. Now we turn to the datasheet to see how we're going to control this thing. What can we actually do with this chip? Chapter 7.3, register definitions. This is very standard. We just have basically a summary of all the registers. And really, it's these first 5 registers, maybe even the first 2 registers, that are interesting. Basically, every other register after that is just controlling some characteristic for the driver. It's controlling one of the channels. So I think our first port of call is going to be this mode register 1. A lot of datasheets will often have like an example program or example pseudocode to show you some typical application. You know, they'll say, write this value to this register to power on the chip, write this value to this register to configure it the way you might want to configure it typically. Unfortunately, this datasheet doesn't have that, so we have to be a bit more careful. If there are any datasheet writers out there, I love it when you include typical application programs in the appendix of your datasheet. Mwah, so useful. So here we have the mode 1 register, and there's some really interesting stuff in here. We have a restart bit, but this looks like it's just the status of the restart logic. When you power on a chip, it'll go through a power on reset, and this is probably just a flag for that. We have the external clock, which is default 0 to use internal clock. That's appropriate. We don't want to include any circuits that we don't have to. Interesting that register auto increment is disabled on startup. We'll probably come back to that later. And when we start the device up, we are in sleep mode. So I guess the first thing we need to do is wake up the device. The oscillator is off by default. And then there's a few other flags for whether it will respond to sub-address calls. Not interested in that right now. So step 1, let's wake up the chip. Or rather, step 1, let's enable the oscillator. Everything else here looks fine, except the sleep bit and the auto increment bit. I think we want that to be enabled later on. So enable oscillator, auto increment. And we have self.i2c, so we have access to all the i2c methods, like write to mem. Self.i2c.write to mem. First argument is self.address. Second argument is the register, and we are looking at register 0, and we want to write a 1, 8. No, 1, 0. So that will be 1, 0. Michael from the future here. There's a very insidious bug on the screen right now. See if you can figure out what it might be. That will be the 5th bit, and the bottom nibble is all zeros. I press Ctrl-R to run the script, and nothing happens. And that's actually good, because this command would have failed if we didn't have everything else correct. So the fact that the REPL returns nothing means that we were able to, we were able to configure our microcontroller. We were able to initialize our class, or initialize our object. And to do that, it means we needed a successful transaction on the bus. So this command worked. We wrote a 1, 0 to register 0. And we can just put in some helpful debug test, setup complete. And there it is. Great. Our device oscillator is enabled. We're ready to start driving our servo. So how do we do that? Every other register on the device is really just the PWM control data. We have a lot of replicated registers where we have LED 0 on, and that's the lower byte, LED 0 on high, LED 0 off low, LED 0 off high. So it looks like for every PWM channel, there are 4 bytes to control its behavior. So we scroll down to example 1. This is as close as the datasheet gets to a really helpful example code. For every PWM channel, for every LED channel, we have 2 control parameters, the on time and the off time. And together, they will set the duty cycle. And the duty cycle is how we control a servo. So our oscillator is constantly counting from 0 to 4095. Our oscillator is driving a counter. And when that counter reaches 4095, it just rolls over to 0 and starts again. So this is like one control window, one pulse in that pulse width modulation. When we set our on time, what we're setting is the number that counter is at when our signal goes high or our LED goes on. And then when we set the off time, what we're setting is the value of the counter for when that waveform goes off. And so by changing these 2 parameters, we can control the duty cycle of the waveform. Now, it seems like the on time is not really necessary for our application. We just want to control duty cycle. So we only need to do that with 1 parameter. we could fix on to just always be 0. And then we can control our duty cycle by changing the off time, and that would change our pulse width. Okay, so we have our control scheme. We need two numbers, the on time and the off time. They are each defined by 2 bytes. And so we need our 4 control bytes to set our PWM duty cycle. But we don't actually know what frequency this is running at. Servos will only accept a pretty narrow range of frequencies, and we have no idea what the actual frequency of this waveform is. So we're going to need to set the oscillator, or the prescaler. Perhaps I told a lie. All the way down the bottom of the register map is register FE, and that is the prescaler for the internal oscillator. We need to make sure that we have a compatible frequency. Now, most servos run between, say, 50 to a couple of hundred hertz, and so we're going to need to load a value into that register to set the waveform to about, say, something in that range. And luckily, the datasheet provides us a formula. We have the value that we need to load in given by this formula. So let's just fill it in. I'll even use the REPL for this. Why not? So we have round. Do we have round? Yeah, we don't get round. Import math. Oh no, we do have round. So we need to round the oscillator clock, which is 25 megahertz. So 25 E6 divided by 4096 multiplied by our desired update rate. I'm going to go for 200 hertz. Times 200 hertz. And then we take 1 off that. And of course, it helps if you don't make a typo or a second time. Okay, so we need to load a value of 30 into that FE register, into the prescaler register. We need to go to register FE, and a value of 30 is 1E. Now, if we read a little closer, this is super important. If we read, it's so important, I'm going to highlight it. The prescale register can only be set when the sleep bit of mode 1 register is set to logic 1. The prescale register can only be set when the sleep register is... We have to actually set the frequency, the prescale, before we take the device out of sleep mode. So we can take this and put it above our enable call. Run the script. Seems to have worked. Cool. And so now there really should be nothing else except loading a value into those high and low time registers and driving our servo. For that, we're going to need a method. I'm going to call that PWM. Of course, it's a class, so we have self. We want to drive a specific channel of this motor driver. So I'll put in a channel argument. And for on time, I'll just set that to default to 0. And I guess for off time, I can default that to 4095. Why not? We're gonna use values anyway, but I guess it might be useful to have defaults. So we have our two numbers, and we want to package them up into a 4-byte message. My servo is connected to channel 0, so I can start at address 6. And we have on low high, off low high, which is little endian. So we want to package in data is equal to, and I guess we're going to need to pack the data. So we're going to need to import struct from ustruct import pack, and maybe unpack. We might use that later. Data equals pack. Now we have the format string for pack. We have little endian, and then HH for 2 16-bit numbers. And then we have the data that we want to be packed. So we have on first, and then off. This is going to take our two numbers and package it into 4 bytes, little endian. And that's ready to go straight off to register 6. And we should auto increment through 7, 8, and 9. Self.i2c.write to mem. We have our self.address. We have 0x06. and we have our data. Now we know channel 0 starts from address 6, so we don't have to hard code this to our channel that we're using today. We can actually say channel 1 is going to be 4 bytes down the line, and channel 2 is going to be another 4 bytes down the line. So we can actually write to 6 plus 4 times channel. And this way we'll be able to write on-off data to any of the channels, even though we're only using one today. And we should now be ready to go. We should be able to get some signs of life. So if I made an infinite loop and said deriver.pwm channel 0, I'm working on channel 0, and off could be, I don't know, 2000. That's about 50% duty cycle. And we sleep ms for a second, and then deriver.pwm 0, and I don't know, 1000 is, okay, a 25% duty cycle. These are within the range of servos. We're of course going to need to import sleep ms. That should be it. We should get a servo that moves back and forth. Fingers crossed. I mean, we'll see. We'll see. There is no servo moving. Okay, we got some work to do. Oh, count the ways in which I have been a silly boy today. This is not how we write hex 1e as a byte string. A byte string should look like this. B quote backslash x1e. That resolves int.from bytes. That resolves as some number. If we have 1 byte from that, we get 30. But what do we get? What do we get from whatever the hell I've written? Oh, well, we get some hot garbage. So that's one problem. Backslash x1e, backslash x10. Okay. I'll power cycle the chip because we've just completely filled it with yucky business. Okay, we still have nothing, but at least we're writing meaningful data to our chip. Great start. Let's just check our sanity real quick and start the program off with a reset of mode 1 register. So that would be register 00, and we want 00. Then we want to put a device to sleep to set, so that we can set the oscillator. Because here we were assuming that it was asleep, but we need to make it asleep. So we need 1, 2, 3, 4, 1, 0. And it looks like this line here where I had 1, 0 before, I thought I was doing the auto increment. I'm not sure what's happened there, but that's all this is doing, is putting it to sleep. So we're going to do a hard reset, and we're going to put it to sleep, or disable oscillator. Then we're going to pre-scale the oscillator to 200 Hertz. And this is clearly wrong, because here I use the same code to disable the oscillator. So to enable the oscillator and auto increment, so we only want to set bit 5 on, bit 4 we want to set off. So we want to set this to hex 20. Yeah, I guess there is nothing for it, but another moment of truth. There have been about like 3 or 4 off-camera moment of truths, but let's give this one a bell. And there you have it. We have a hello world. We can drive this device. It's not much at the moment. We're using, let's turn this off. It's not much at the moment. We're using these naughty little byte strings to just write constant values. It would absolutely be better practice to read the contents of a register, set the bits you want to set, and then write it back. Classic masking and bit logic, basically. But this is enough to start with. I'm going to implement some real quality of life improvements now, so that we can not do silly things like have to use byte strings, etc. We can probably time lapse this out, and I'll see you in a few minutes. Okay, first quality of life improvement, internal read and write methods, because having to constantly call self.i2c.write to mem, self.address, the register, the value sucks. We just want to write, in the case of the reset, mode 1, we just want to write to register 0, the value 0. And so we have a method for write that basically wraps the write to mem method, and a similar method for read, which wraps the read from mem method. So here I have commented out the old command, and we have the new command that I've checked things are still working. So we're writing the correct data. That means that these two commented out commands we can remove. And this just looks so much nicer. You know, we can make some much more readable code now. You may not be able to hear it, but this servo is kind of freaking out. It's kind of constantly vibrating. And I think that's because our frequency may need tuning. These PWM values I think are fine, but we may just be sending the wrong frequency. And so in the course of fixing that, we may as well write a real frequency setting method. I think that's probably a good place to wrap up. We have a pretty clear direction of some housekeeping improvements to make helpful functions for things like setting the frequency, and maybe even helper method into something that's more of a servo angle method, because that's really what we want to do. We want to control a servo angle. We don't want to have to think in terms of this raw pulse width variable. Boy, did we go down a rabbit hole in this episode. I probably didn't do the best troubleshooting that I could have. You know, looking back, should have busted out a logic level analyzer perhaps, should have looked at some waveforms on a scope. Hell, even just reading back values from registers to make sure they were being set correctly would have been a really good start in debugging. But hey, I've made these mistakes, so you don't have to. If you've made it this far through the episode, you're clearly one of the top factory fans. This bit's for you. We're going to put firmware development to the side for a little while and work on the PCB in the next episode. And we've already got a couple of ideas of how we're going to do this, and we're going to share them in a forum post so you can weigh in on whether you think they're good inventive ideas or terrible standard breaking ideas. I really look forward to hearing your thoughts, and this could be your chance to help us make this product exactly how it ought to be. As always, if you have any questions, leave us a comment below or on our forums, and I look forward to seeing you in the next factory episode where we will begin designing the PCB. Catch you next time.